Welcome. This lecture is part 2 on the flow performance of an electric submersible pump. In this lecture, the main focus is hydraulic efficiency. So consider here you have the diagram of a vertical well that has an ESP installed in the tubing. Here I have tried to make it more clear that I put here the pumping part, all the impellers and all the stages, and then you have a shaft, and then you have a motor, and you have the cable that provides power to the motor. So you could visualize it like some power is coming from the VSD drive, minus of course the losses of transportation through the cable, which might be a very long cable, 3,000 2,000 meters, and that enters into the motor, and the motor produces some shaft power. So there you might have some losses. Typically P shaft is not the same as P motor, so you have an efficiency. Sometimes I use the term mechanical efficiency, that is the P shaft divided by the P of the motor. Okay, whatever power is entering into the motor and whatever power is coming out, there is a ratio between them. This is less than 1, and this number is typically close to maybe 0.95, 0.98. So it's a very high value. There are actually very little losses in the motor, but it's something we have to take into account. Now comes the second part, which is the hydraulic efficiency, which tells you how much from that shaft power is actually used for pumping. So here you have the P shaft, and here we have some power that is required for pumping. Let's call it and we want to find out how that looks like. How does that efficiency, how this guy looks like, the P that you need, the power that you need for pumping. So for that, we're going to apply the first law of thermodynamics for open systems to this system that I'm going to highlight with a red line here. So if I apply the first law of thermodynamics for open systems, I have that the Q plus work plus the energy coming in minus the energy coming out is equal to 0. The pump typically, the purpose of the pump is not to exchange heat with the environment, although I might have some losses, but typically I assume these are negligible. Here I have W, whatever is coming in, which is the shaft. This W essentially is the shaft power. So this tells you that this will be E2 minus E1, and then I take out as a constant the mass flow, and then I multiply it times the specific E2 minus E1. The specific energy, we know it consists of different terms. We have G times Z, the elevation. We have the kinetic energy term. And we have the enthalpy. Don't be confused with head. This H represents enthalpy. Okay, so typically in a pump or in a stage, you might say that the change in elevation is negligible. The change in kinetic energy is also negligible because it's a fairly incompressible fluid, so you have some change of the change in pressure causes some changes in density, but not to cause a significant change in kinetic energy. Okay, but then you have this guy here, H, that enthalpy, that actually this is U, the internal energy, plus PV. So if I consider an ideal pumping process, that means that I have no irreversibility, no non-idealities, I have no friction, I have the process, it can be reversible, then in that case I might say that the process is isentropic, which is delta S is equal to 0. That's the ideal pumping process. That means that that's the one that will require the smallest amount of work. If I do that, then the delta U is equal to 0, because for an ideal liquid, U is a function of temperature, and you don't have any increase in temperature in this isentropic process. So then you end up that the work ideal, the pumping power, required power for an ideal pumping process is equal to mass flow times P2 V2 minus P1 V1. You can also further assume that the V is relatively constant, the density. This is the inverse of the density. Yeah, and then you end up with the following expression. That will be Q, M divided by density is Q, P2 minus P1. So that tells you that this is, if I were to pump it ideally, that means isentropically with no change in temperature, this is what it will require. And the shaft power is telling you what actually it is requiring, how much energy it is requiring. So then the hydraulic efficiency can be expressed as Q times P2 minus P1 divided by the power at the shaft. And typically this is going to be a number, maybe sometimes between maybe 0.4 if you have a very poor um, pumping process, but maybe all the way to 0.8 if you have a very good, very efficient pumping process. Okay, so that means that 60% or 20% of the power that you introduce is being lost due to some non-idealities. Okay, these non-idealities might be, some of them is friction. Okay, we have friction with the vanes, for example. We have friction with the back of the impeller, okay, which create heat. We also have volumetric losses, okay, in which the fluid might want to go from regions of high pressure to low pressure, so it might want to backflow through the pump. So all of these phenomena, they cause that, and you also have friction and turbulence. And eddies, formation of eddies. And all of these phenomena, they actually cause that the process is not ideal. It's real. The efficiency curve then looks something like that. Okay, the hydraulic efficiency curve looks something like that. So we have the fixed frequency. If you're changing the rate, you will see that there is a point at which I get the maximum volume hydraulic efficiency. And then if I increase the rate from that point, it will start to go down. And if I decrease the rate from that point, it will start also to go down. So it's like the pump is designed to be working at the best efficiency point. That's the design point. But then if I go away from that design point, then the efficiency, hydraulic efficiency, is going to go down. And a way that we could visualize that, here it's a slide from a presentation where they did measurements of the flow in the passages of a pump. Okay, here these are not the impeller, but these are on the diffuser, but essentially in the impeller you have a similar situation. So you see here that we are operating at the best efficiency point, the rate, and at that point the rate that you have and the velocity that you have of the flow approaching the vane is actually going to be aligned with the passage. So then you have that it flows smoothly through the passage, and it follows the contours of the passage. But then when you, in this case, you reduce the rate, then the fluid is not aligned anymore. The velocity of the fluid is not aligned anymore, but it's going at an angle. And because of that, then you have some detachment of the fluid from the walls, and then you create these local recirculation places in which you have turbulence, you have eddies that they dissipate energy. Okay, and you see here, if you reduce further and further, then you have a greater recirculation area. So the efficiency curve can often be expressed using a polynomial, just like the head. So you have that the efficiency is equal to some coefficient. If we use a second order polynomial, it will be something like that. Okay, but typically I need a higher order to capture properly the changes on the curve. So the most important application why I need to use efficiency is to calculate what is the power of the motor required, the capacity of the motor that you require. So for that, first I calculate first the shaft power. which will be the delta P times Q divided by the hydraulic efficiency. And if I have the frequency, I have the rate, then I have the hydraulic efficiency, and then I have the delta P. I can calculate the power, the shaft power. And then after I have the shaft power, I can calculate the motor power with the mechanical efficiency, which is W shaft divided by mechanical efficiency. And this guy here now is the motor I have to design for my pump. The capacity of the motor I have to design for my pump. Now, so far we have seen that this curve is for a fixed frequency, and then we all are also interested to see how that curve changes with changes in frequency. So let's take a look at that. So that is performed using the affinity laws, and that's the same thing we have used for rate and for head previously. This is called similarity or affinity laws. Okay, but now I have another element here, which is this P, this is the shaft power. So we can say that the efficiency, hydraulic efficiency of the reference is equal to the Q of the reference times the delta H of the reference. These are all at reference frequency divided by the power, shaft power at the reference. And then we want to convert that point to the efficiency at any frequency. Okay, and for that I need the Q, actual Q, the delta H reference, no, not reference, but the delta H at F, and the P in the shaft. And we know we can convert, we don't know how to convert efficiency, but we know how to convert all the different values that you have here, all the different Q, delta H, and power. So to do that, this will be the Q ref times the F divided by F ref, and this will be the delta H ref times F divided by F ref squared, and then I have the P shaft ref at F divided by F ref to the power of 3. And what happens here, if you see that these terms, they cancel out, so it tells you that essentially the efficiency, the hydraulic efficiency at any F is going to be equal to the hydraulic efficiency at the if reference. So there's no need to correct the hydraulic efficiency for frequency, the value of hydraulic efficiency. But there is a small nuance here. So let's assume we have Q, and we have our hydraulic efficiency curve, and we have, let's say we have these 5 points. Okay, so that means that the value of the hydraulic efficiency shouldn't be corrected with frequency. This is for reference frequency. Okay, so if I have another F, simply the value will remain the same. It will remain at the same Y. Okay, let's say we're converting this point here, number 1, which is the best efficiency point. Okay, but the Q of that point 1, here we have efficiency of 1. So efficiency of 1 star, okay, that is at F, is going to be equal to the efficiency of the point 1 at the reference frequency. Okay, but now the Q, actually with the Q we do have to change it. So the Q of 1 that is made at an F reference, and I want to calculate the Q of 1 prime at a frequency, this is going to be equal to the Q1 at the reference frequency times F divided by F at the reference frequency. Okay, so that means at that point, if my frequency is higher, then that point will move horizontally, and you will find here a new point called 1 prime. Okay, and the same thing will happen with all the points. You have here another point, you have another point, and here you have one more and one more. And what happens is that the efficiency curve just shifts to the right if the frequency is higher, or the efficiency curve shifts to the left when the frequency is lower. Okay, you have a shifting of the curve to the right or to the left. Okay, so if that's the case, it tells you that for a higher frequency, the rate is going to be higher. And the rate at which I have the best efficiency point is going to be higher. Okay, this is Q1 star. So now after we have this knowledge about hydraulic efficiency, let's go back and see at the whole performance of the map, how it looks like now with all the things that we have learned. Okay, so it looks something like that. You have this type polynomial shape for one fixed frequency, this green curve. You have the relationship between head or delta P with local flow rate, Q. Then if I increase the frequency to the maximum, I will have an upper curve, an upper limit, which might be 60, 70 Hertz. And if I reduce the frequency to a lower value, then I will have this lower curve. Then you have, due to this issue that was mentioned before, you have the floating impellers. If the flow rate is too high, then the impeller will tend to touch the diffuser. This part of the diffuser will have high friction and heat, and then you'll have early wear. That may have early failure. And if you have the opposite, then very low flow, then the impeller will rest on this diffuser, and then it will also create wear and early failure. So these two is called up thrust and down thrust, and they occur at some rate for each frequency that this is rotating. And these are the two lines that I have here to the left and to the right. Okay, so they defined the maximum rate. I shouldn't exceed that rate because then I will have too much upthrust and then I will have early failure, or I shouldn't go below that rate because then I will have down thrust and I will have early failure of the pump. Okay. You could also see that this is also sometimes not because of down thrust but up thrust, but I want to maintain a given efficiency for the pump. And I know this reduction it sometimes might be quite dramatic, and I can also make some limit based on that I want to achieve certain minimum efficiency. And here you see the best efficiency line, which is joining all the best efficiency points for each frequency. And if you remember, we have for the reference some frequency. In this case, it's located, the maximum point is located here with rate. But then if I increase the frequency, then that point, as we mentioned before here, is shifting to the right. Let's say we increase the frequency to that value, then the point, the Q increase from here to here. Okay, the best efficiency point. So this is the line joining all best efficiency points for all frequencies. And at the end, you end up with operational region due to all of these constraints that looks something like that. So if you have the delta P or delta H of the ESP, and here you have the Q, you have the maximum frequency, the minimum frequency line, and then you have the maximum rate and the minimum rate line. Okay, the up thrust, down thrust, or minimum efficiency limit. Okay, so this is going to be the operational area of the ESP. So as an example, I took an image from a paper that we're going to use on a following exercise. Okay, this is for a offshore field called Peregrino. And here you have the different models. These are different models of ESPs. These curves are made for one centipoise. You see all of them are for one stage, but they are for different types of pump. Okay, you have head and feet. This is one stage. Okay, so you see here you have the Q and here you have the head. You see here it's around 50, 60, so it's around maybe 20 meters that you have for one stage. And you have the maximum frequency, minimum frequency, maximum rate up thrust, and minimum rate down thrust. So the point should fall inside that map. And if your point, for example, your operational point tells you should be here, you see that only the black and this green work, none of the rest. But if you are here, then you see that only this the pink one will work. So this helps you also to try to define which pump is the best. Of course, during the life of the field, typically you have a variation of the delta P of the pump and the rate that it might move. So in that case, you have to find the right model in which the point operates properly. This comes from this paper. Okay. As a last comment, I have also to say that the viscosity of the fluid affects the performance of the pump. You have, for example, this is for 1 centipoise that we have mentioned before, but then if you have 10 centipoise or 100 centipoise, then the head is going to be reduced and sometimes quite significantly. And that's because the friction, you create a lot of friction with high viscosity, and then you have more pressure drop, and then the head actually simply is reduced. To find out the new curve, we cannot apply a similarity loss as we have done for frequency, but then we have to use some correction method which is highly empirical. And one of them is this from the Hydraulic Institute to how to correct centrifugal pump, but there are many more. Some people have said that this is not so accurate, the 9.6.7, but this is required if you're handling high viscosity liquids. And we're going to see that in our exercise in the next video.